And I think what our purpose here is just give everybody an opportunity to share some things on this. And so next on my list, Mike, why don't you tell us what's on your mind?
As you might have noticed, we weren't one of the blue states up there. We were one of the gray states. We're using Dayton DTIMS to do some of our predicting modeling. And I agree, you really have to make sure that you look at your model. You can't take things straight out of it. We did a lot of testing when we did our modeling. You find little things they just don't think about. It's like the first time we ran it, we found this one bridge and we said, we're going to follow this bridge through 40 years and look at recommendations for 40 years. And we said, well, here, it was replaced. Well, it's still going on. 20 years later, it's replaced again. It's like, what happened? That shouldn't work. And it was a timber bridge, and when it replaced it with another timber bridge. So it's like, okay, so we fixed that problem. But there's little things you have to look all through that model. You can't just take the data out of it. And we found if we let the model try to optimize, it gave you a lot of polymer overlays up front, you know. And so what we ended up doing, that's not how we're going to do our work. So we started looking about what we would do for polymers, hydros, and those are the things we focused on because like I said, not everything is going to be used. So we did polymers, we did overlays, and we did joints. And that's sort of what we focused on in our model. And so we kept it real simple and came out, the more we worked it, the better it looked like it was working. And so far, we've done what we did. We tested our model. We took our 1992 data, bridges that were how they existed in 92, and since we did no preservation until recently, we could just run those through our model and do nothing to them and see if it predicted how well it predicted, and actually did very well. We were almost spot on poor, and we were predicting good bridges too much, and so we had more fair bridges than good bridges. So we were really close, happy with our model. But once again, we don't take everything that comes out of it, and that's what we do. We use it for modeling, and we still, when we pick a bridge, we're still looking at it. We're looking at the inspection data ourselves. We're kind of the opposite of Florida. I mean, they have a very nice, expensive system, and we are a little bit less money because our bridge program, we're about $90 million a year. That's all. That's our whole bridge program, and about 20% of that we're spending for preservation. Now we get a little extra preservation money. We steal some from pavement preservation. You know, they get about $300 million, and they allow us to take about 10% of that money and look at bridges inside their corridor where they're working, and we get to do some preservation on some of those bridges. You know, so our funding is a lot less funding. It is getting a little better. One good thing that came out of COVID is that they gave the departments some COVID money, and we got about, I think they gave our department like $120 million of COVID money, and they decided to put $50 million of that towards bridge preservation. Not replacement, but preservation, which is really great because now we're tackling some of our bigger bridges, you know, like the Highway 49 bridge crossing the Mississippi River. That's like an $18 million project. We wouldn't have had the money to do that for years, and now we'll be letting that job probably next year. But we're doing a lot of looking at it individually, so it's time consuming for us to look at so many bridges, but that's kind of how Arkansas is running their program right now.
And next, Andrew, do you have some thoughts you want to share?
Hello, I'll just talk for a few minutes. As Jeff and Aaron explained, at least on the state side, we're pretty good, pretty ahead of the game. It's about give or take about $100 million a year for routine maintenance and rehabilitation. On top of that, if a bridge gets to where it's condition state 4 NBI or less, or it's posted, we'll go ahead and replace it in 6 years. There's a whole other series of conditions where it would be considered for an economic replacement if it costs too much to upkeep, and that's about a 10-year idea. Our work program, we do use some fancy things with BRM but it's mainly a 5-year projection to where it's a bespoke thing. You sit down and let the data inform decisions, but the general program is 5 years out. I would say in Florida, our weaknesses are mainly with local bridges. It's a federal program. It's for replacement. We have a nice system to rank bridges for replacement, but the fear is, are we rewarding bad behavior? If I'm a local owner, does it pay just to let it go to heck, and then I can get it replaced? And we're looking at some better ways to spend some money there. We could always use more money for the local bridges also. The other part, and I specialize in load rating, in permitting. What I wonder is, with all this, these numbers, how can I convince people that it's worth doing strengthening? If I can put some real numbers on that, if it's a good idea for me to let a crane go down a highway versus reroute 50 miles, how much is that going to cost for, several cranes a day over 10 years? But that's just some thoughts, and welcome your questions later.
I think it's just such an exciting time. I'm a bridge management system geek. Anybody who knows me knows that. And I waited 20 years when I was at Michigan DOT to see operating bridge management systems. And now they're operating. And now we're starting to learn, okay, what they're doing good, where we're still having some challenges. And it's just, and then there's new systems coming online all the time. With that, I have Isan, who works for Bridge Intelligence, and he's going to show us their system that they're working on and have developed.
Thank you, Dave. So what I prepared today was not about actually showing what we are doing, but mostly the points that I came across and I found very useful for application of these sort of preservation decision-making frameworks. But before that, I should provide you with an overview that I prepared, and I hope it can help with implementing these sort of decision-making frameworks. This is the overview of or definition of preservation decision-making frameworks. These are pretty much frameworks that determine the right time and the right preservation action for bridges and culverts within a specified program period, with the purpose of minimizing long-term costs, together with minimizing serviceability interruptions. So, but during this process, we have multiple constraints, especially if we are looking at large-scale frameworks. Those are first ensuring safety, staying within our available budget. We don't have all the money to do all the preservation actions that we need, and also we need to satisfy performance measure constraints that we are usually facing. They are either federal performance measures, like the 10% penalty for the bridges that we submit to FHWA, or maybe they are state performance measures that is set by our legislators, and we need to satisfy them. Traditionally, these processes were used to be done in separate silos, partly, but now that state DOTs are moving towards more advanced and holistic frameworks, we are facing systems that usually comprises 3 parts. The first part incorporates multiple input models. Those are mostly the current bridge and culvert information, action possibilities that we can have or we can think about for our bridges or components. We had a lot of good presentations today about new technologies, and we're going to have more in the coming days that talk about new technologies. So if we could recognize them, know their costs, their amount of improvement they will incur on our components or elements, and also deterioration models following application of those actions, that would be a great step for having realistic and more advanced decisions that we can get out of these holistic frameworks. We feed this information into those frameworks through an optimization engine, which is usually a mathematical framework. So as Zach said, there are incremental benefit cost ratio frameworks, or there are other frameworks based on integer linear programming. that can be used, and those frameworks give us output results, which are actually what we are looking for. What are the optimal actions, and what are the right time of applying those actions? Having said that, these are actually the points that I came across, 3 different systems, bridge management systems that I was working on, one for Ohio DOT back in 2000, from 2016 to 2018, and then one for Virginia DOT in the 2 years that I worked for them, and one that I finished the first draft without user interface though, for bridge intelligence. So these are the points that really help us to have more realistic results and more advanced results. So first thing is to improve the input models, reducing the errors in our input model. We know now, these days, we have a good amount of data, take advantage of them, and develop good deterioration models, cost model, and also the improvement models. Then considering user cost to account for the intervention of the repair actions that is put on the public really adds to the realistic results that we can get out of the framework. Third is considering minimum value for cost of projects. This is also really important because we all know there are hidden fixed costs, MOT costs. We have engineering or PE costs. We may have right-of-way costs. Those add to the minimum bare cost of projects that make them to be, let's say, more than $20,000 or $25,000. And this prevents the framework to give you small piece of, small projects that does not look realistic. And the fourth point is to consider safety thresholds. We are now thinking about minimizing life cycle costs. So the discussion is a lot about cost. But then we should not lose the sight about the safety of elements. So if we can set some thresholds that mandates element or component replacement instead of considering multiple project possibilities for them, that would give us what we are actually looking for. And lastly, but not least, choosing objectives that gets us closer to what we want from our framework. So we want to be life cycle cost efficient. That would be one major objective function. And the other thing is considering risk of hazards, especially floods, and especially for those bridges that are exposed to repeated occurrences of those floods, in addition to the gradual structural deterioration that we mostly talk about. So with that, I hope these things help you with more successful implementation of bridge management systems, and I would be glad to take your questions.
I'd like to open it up to the audience for questions. Now, our topic here, of course, is preservation, and how that is the value of preservation is being showed with bridge management systems. So anybody, just raise your hand if you have any questions or topics you want to discuss on this.
When you're thinking about life cycle cost of preservation actions or repair actions you're talking about, how is that model taking into account the life cycle cost of preservation action? Are you talking about the life of the action and how many times in terms of the end of service life? What's the salvage value? How are you doing all that, get it to the present worth? Are you comparing different actions? How do you do that? I'd like to get more information.
Sure, and each of the bridge management systems probably do it a little differently, but I saw Zach jumping at the opportunity to answer this one, so we'll give Zach first opportunity, and then we'll let the other panel members.
Yeah, that's a really perceptive question. You're absolutely right that there's a few different ways to approach that. I think for everyone with the life cycle cost by definition means you're summing up all of the projects over a certain time frame, and then that residual amount, or as you call it, salvage value, about the same idea, at the end. With BRM, in order to come up with all of that, we actually require the users to put in what is their typical maintenance and repair cycle, so that we can calculate, as a result of this, does it push back the other ones or invalidate the need for painting or other repairs, and then how does that change the residual value at the end, if that makes sense.
Looking at two different ways. If you don't do anything, what are the actions that they have to take? What is the cost of those actions? And then if you do this, how would that change or to push that back?
Exactly right.
So for example, if you do an overlay, if you don't do an overlay, then you'd be patching and you would do a certain every 3 years, 5 years, or whatever.
Until replacement.
You calculate
Exactly.
the cost.
Yes.
If you do the overlay, then you won't do the patch, but you would have the overlay life 20 years. And after that,
Right.
even during the process, every 10 years, you do something. At the end of 20 years, you replace the overlay. And you do it twice, you get the overall.
Yep, exactly, yeah.
Ours is a little difficult to explain, but what we do, we do a do nothing, and that gives us a curve, and it's based on, as the NBI values. So there's our curve with the NBI values dropping. And then we do the treatment, say maybe it's a polymer overlay. Well, that doesn't immediately do anything to help you, but it follows the curve. But then when this first curve would do nothing, it drops down because your deck has deteriorated. We gave a value, say, well, 12 years is before that deck now drops down. So now there's a difference in those two curves. So we take that area between those two curves of doing nothing and doing a preservation activity, and we take it out for 40 years. So we basically gained a little bit more life for that deck, and that's just looking at the deck for that time span. It will eventually drop down, but it stayed in a better condition for 12 years. So we take that area, and that becomes a benefit. And the benefit gets a little confusing because our benefit is an improvement of our NBI numbers. And then we have the cost. We put all our cost in there. So it's a benefit cost ratio. So we take that benefit that area gives us, and we divide it by the cost of what that costs us to do that preservation treatment. And we do that for everything and all the different treatments, and we get a benefit cost value at the end of the run. So our goal is to have fewer poor bridges. So if something falls in the poor, we quit counting it. Maybe your deck is still gaining value, but maybe the superstructure fell to poor, so it doesn't matter. We chop it off, the value stops when it goes poor. And that's as much benefit as that treatment can get you.
This is from a systemic level. You are
Yes.
looking at it. But when you go to a particular bridge, you said you also look at the data for that bridge to make a decision whether we really want to do that. Because if the system comes up with a whole bunch of, epoxy overlays or something,
Right.
and you don't want to do that. So how do you
We
differentiate
limited
that?
the system because we tried the system to let it pick everything. And it really loved polymer overlays early in the system, and then later on, it was doing hydros and stuff like that. We just had to look what was more realistic. We're not going to spend, because our money is our replacement money too. So we really had to first pick some criterias, and we ran 30 different models and came down percentage-wise what was the best for replacement and polymers and hydro demolitions. And then we looked 40 years and said, what does it look 40 years from now? And that's how we picked how much money we spent in preservation or rehab or polymers. We had to define some rules because if it tried to do everything itself, it wanted to do all the polymers right at the beginning, and that would never fly. So we had to limit what it would do.
Regarding that repeated actions that the software gives, I want to share with you my experience at Virginia DOT. So they had these caps for each of the actions that they had, for rehab and for repair, and they would break it down for 15 types of structures. So based on their real life experience, they could come across, let's say, 2 times of repair and 1 time of rehab for this specific type of bridge. And that was the key, not to have repeated actions. And I assume that it's the practice out there.
How many times that they would do something and then they stop it? Like, is there a criteria for that? It doesn't depend on the life
I
of the
wasn't in the
structure?
process of developing those criteria, but as far as I can say, and I can guess, is that these were based on the database that they evaluated. They figure out that after, let's say, 2 times of repair, it is not cost efficient to do a repair again, or it is it has so many damage that you cannot do a repair anymore, so you need to leave it a little bit more time and do a rehab.
The ones I'm familiar with are bespoke, bridge by bridge. Just a lot of money on the line. To keep a segmental bridge going for a while, go ahead and replace it. For a movable bridge, to keep paying a tender, or go ahead and do a high level. For a substructure that's going, or go talk to Ivan and see if you can do cathodic protection. But there's no sweeping program for such expensive projects. And generally, it's present-day cost.
Probably want to look at the bridge itself instead of doing the modeling. Modeling helps, but you really have to look at the bridge. But this was for general bread and butter type bridges, I guess.
I could be better at that. I could probably talk to him.
My question is about the deterioration models, and you know how each action that you do has a change in that deterioration model. And I'm thinking about, you know, the local bridge owners. As a consultant, we often have to try to talk with them about preservation and how that makes sense. But it's very difficult when we don't have these complex models to do that. So, you know, we make assumptions on, you know, what this action is going to do to change the life of this bridge, the life cycle cost, how long it may extend the life, things like that. But it would be good if there was more collaboration, I think, within all of us, that we could share that information so that we could look at these different actions and have maybe a range of potential outcomes for those actions that we generally agree upon within our within our group. That, I don't know if this is a question or a comment, but that's my thoughts.
All of the advanced bridge management systems that predict the future, you need to input your deterioration models. And so there is some research out there. The Midwest Bridge Preservation Partnership actually has a research project ongoing right now. So somebody who does that sort of thing, I'm anxiously waiting for that. You're right. You have to be able to put in good deterioration models to be able to predict the future. So with that, I think we're close to our time to end. And I think it's really exciting that, you know, part of this group, which is bridge preservation, is talking about the bridge management systems. And I do understand that sometimes there's some confusing terminology. You know, we start talking about life cycle cost, and we start talking about benefit cost analysis and optimization, and even I haven't heard the term efficient frontiers, one of my favorite little buzzwords. You know, I encourage folks, and people are having to do it because they need to do the TAMP, which requires you to predict 10 years out and set targets and identify your gap. But also agencies are getting more detailed and saying, okay, help me identify which structures I need to work on in next year's call for projects. And I'm going to put in one little plug for the Federal Highway Administration is starting up their 3-day bridge management system workshop. And so if you're interested in that, to learn a little bit more about some of these topics that the panel discussed today, give Derek Constable a call. With that, I think we can end this session.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.